on to Unit 7, rational versus irrational numbers. This one's going to be pretty straightforward. It's going to be pretty easy. Just telling the difference between two different types of numbers here. We'll jump right into rational numbers. Okay, some of you probably seen this before. Mr. Bartlett in years before had a story of the history of numbers versus counting numbers, whole numbers, integers, and real numbers. Okay, may or may not be true, but let me see if I can get this story straight. One thing I know for sure is we have two of these prehistoric characters here. We'll call this one Ugg, and I think this one looks like a thug. Alright? Now, these guys are hunters. In the prehistoric days, they'd go out on their roundabout or wherever, and they'd talk to each other. They needed a way to communicate how many, maybe woolly mammoths they saw in a day, or maybe a saber-toothed tiger, maybe a long-haired liger. I don't know the animal, but they needed a way to communicate what they have going on here. Okay? And so they came up with counting numbers. Alright, maybe I saw one woolly mammoth, or maybe I saw two saber-toothed tigers. And so, counting numbers became numbers like this, and then on and on and on. It would expand. Alright, pretty straightforward. Now the whole numbers evolved from the fact that Ugg went out one day and he was humming his favorite Disney tune at the moment, and he didn't do a very good job hunting. He didn't see anything. He scared everything away. Alright, and so they had to add the number 0. So basically, whole numbers are counting numbers with the addition of 0. And on and on and on. Okay? So now we have counting numbers and whole numbers. Alright? We have this way to communicate. So now we needed integers. Integers came about when these guys started bartering or trading. Okay? And I think one of the scenarios, if I remember right, was Thug had a woolly mammoth. And then he preferred maybe a long-haired liger meat to woolly mammoth meat. Okay, so Thug had a woolly mammoth to trade Ugg. Alright, now obviously a woolly mammoth is going to be substantially bigger than a long-haired liger. So, maybe they decided it took 7 long-haired ligers to equal 1 woolly mammoth. Alright, well, Ugg didn't have that to trade, and so they kept a tally. And once they did some trading, maybe they agreed that Ugg was in the hole a little bit, or we introduced negative numbers. So maybe after that trade, Ugg was a -2 to Thug. So that's how we introduced negative numbers. And the negative numbers, with the addition to the whole numbers, became integers. And this would go on and on and on from both ways. Okay, so now we have counting numbers, which 1, 2, 3, 4, a whole number, which includes the 0, and now we have negative numbers and the integers. Now real numbers, later on at some times, maybe we had a half of a woolly mammoth. They started to trade back and forth. So real numbers just includes fractions and decimals. So maybe we have -7/2, -1, 0.25, 1, 2, and on and on and on. Okay, so just to recap the history of the numbers with Ugg and Thug here, counting numbers, 1, 2, 3, 4, and on. Alright, whole numbers with the addition of 0, integers we added negative numbers, and real numbers we added fractions and decimals. Okay, and so we look at this graphic here, and let's just focus on real numbers for a minute. We have the rational numbers, alright, which are fractions and decimals. The integers, which was the negatives, along with all of everything below it that you see. Okay, the whole numbers were counting numbers plus 0. Alright, and so if we're looking at this diagram, we have the counting numbers, whole numbers are all included in integers, plus our new thing, which is negative Alright, and so then we look at the rational numbers, includes all of the smaller circles inside of it. Okay, so if we're talking about rational numbers are integers, whole numbers, counting numbers, with the addition of fractions and decimals. Okay, and then we have these irrational numbers over here that we'll talk about. Okay, we'll take just a few notes here and talk about rational numbers. A rational number is a number that can be written as a quotient of two integers. Okay, quotient of two integers, that just means fractions. Okay, if you remember, every fraction is a division problem, and that's what they mean by a quotient of two integers there. Okay, when written as a decimal, rational numbers either terminate or form a repeating pattern. We'll talk about that here in just a second. Alright, on the other side of things, an irrational number cannot be expressed or represented as a quotient of two integers. It can be represented by decimals that never end and never form a repeating pattern. Okay, so by a repeating pattern would be, for example, if I had 1.55555, okay, and so those fives go on and on. Or it could even be 1.4545, okay, where you see that pattern. A lot of times those get represented with a line over top of it. Okay, and so quick recap here, we'll just identify some rational and irrational numbers here. On the rational side of things, maybe 7, negative 9/2. So I want to point out here that negative numbers can be on the rational side. Okay, and then here on this one we have a repeating pattern. Alright, whereas on irrational numbers, if you're not familiar with the square root of 2, okay, that number looks something like, if you punch that into a calculator, that's going to be something like 1.41421356237, and it goes on and on. There's no pattern that ever forms from this. Okay, if we take a look at this next one here, we're just adding 3's each time. Now that's not really considered a pattern for us. There's no way to put a line over top of that that would make that true. And pi, 3.14 is what we use, but that number goes on and on and on, and it does not form a pattern. So that's one of the most famous irrational numbers that we use. A lot of times we just say that it's 3.14, but it is an irrational number. Okay, some examples jumping in here. Show the number is rational by writing it as a quotient of two integers. So once again, we're just going to write these as fractions. Okay, and so on number 1, 7. Alright, if we had to put that into a division problem, we'd know that to just be 7 over 1. 7 divided by 1 equals 7. That's how we write that as a fraction. Alright, on number 2, negative 10, we need a division problem. We need to put that into a quotient of two integers that just equals negative 10, so we're just going to go negative 10 divided by 1. Okay? Because here again, that's going to equal negative 10, and that's what we're trying to represent. Now how about this mixed number here? Do you guys remember how to turn mixed numbers into improper fractions? Just going to go 5 times 4, add 3, so that's going to get us 23 over 4. Well, that's a fraction right there. That's a quotient of two integers. Okay, and so that's all we need to do for that one there. Okay, let's talk about decimals for a minute. If you take a rational number, call it a over b, and carry out the division, the quotient will always be terminating or repeating decimal. Okay, so if we talk about terminating, that just simply means to end. It's going to stop. Okay, repeating, you may have something like this, a line over top of it. That means all the numbers underneath that line will repeat. So if you had a 2.45 and the line was over the 4 and the 5, both, it would go on 4, 5, 4, 5, 4, 5. This does not occur with irrational numbers. Okay? And so as we take a look at this, 3 over 8, remember, this is just a division problem. Every fraction is a division problem. So we would simply pull up our calculators, go 3 divided by 8, read it top to bottom, and we would get something like 0.375, and it would terminate. That's all there is. Okay, so this one terminates. We look to the next one here, we go to our handy dandy calculator, and we'll go 5 divided by 11, and you should get something to the fact of 4, 5, 4, 5, 4, 5, and that should extend on, so our answer will end up being a line over 4 and the 5. This one repeats. Okay. If they terminate or they repeat, they are rational numbers. Okay, now terminating decimals is rational. Prove each terminating decimal is rational. Now, how do we prove this? We can write it as a fraction. We can write it as a quotient of 2 integers. Okay? And so as we look at 0.7, if we say that correctly, we should call it 7/10. If you can read it, you can write it. 7/10 sounds like 7 over 10. Okay? And so we know that is terminating decimal is rational. Okay, we look to the next one here. We have negative 3.05 is how we would say it mostly. Okay, if we say it correctly, we should get negative 3 and 5/100ths. Go ahead and reduce that down. I'll get a negative 3 and 1/20th. Now I need to put it in to a fraction. Take this mixed number, turn it into an improper fraction. I'll get a negative 61 over 20 by going 3 times 20 plus 1, and we keep the denominators the same. Okay, all stuff you've seen before so far. Write each repeating decimal as a fraction. If you want a little extra, if you want a challenge problem, go ahead and tackle this one here. I'll leave this one up here for just a second if you want to write it down. And then email me if you get the answer to this one. Okay, this is a little challenge problem for you. Okay, so basically what we're talking about today, just to recap a little bit, is rational numbers versus irrational numbers. Okay? And to review that just for a second, rational numbers is a number that can be written as a fraction, where irrational numbers never end as a decimal, never form a repeating pattern as a decimal. You cannot write them as fractions. Okay, a quick little review here. Hope you have a great week. We'll see you next time.